Assembly language.
An assembly language is a low-level programming language for a computer, or other programmable device, in which there is a very strong correspondence between the language and the architecture's machine code instructions. Each assembly language is specific to a particular computer architecture, in contrast to most high-level programming languages, which are generally portable across multiple architectures, but require interpreting or compiling. Assembly language is converted into executable machine code by a utility program referred to as an assembler. The conversion process is referred to as assembly, or assembling the code. Assembly language uses a mnemonic to represent each low-level machine instruction or operation. Typical operations require one or more operands in order to form a complete instruction, and most assemblers can therefore take labels, symbols and expressions as operands to represent addresses and other constants, freeing the programmer from tedious manual calculations. Macro assemblers include a macro instruction facility so that, parameterized, assembly language text can be represented by a name, and that name can be used to insert the expanded text into other code. Many assemblers offer additional mechanisms to facilitate program development, to control the assembly process, and to aid debugging.
Key concepts. Assembler.
An assembler creates object code by translating combinations of mnemonics and syntax for operations and addressing modes into their numerical equivalents. This representation typically includes an opcode as well as other control bits. The assembler also calculates constant expressions and resolves symbolic names for memory locations and other entities. The use of symbolic references is a key feature of assemblers, saving tedious calculations and manual address updates after program modifications. Most assemblers also include macro facilities for performing textual substitution, for example, to generate common short sequences of instructions as inline, instead of called subroutines. Some assemblers may also be able to perform some simple types of instruction set-specific optimizations. One concrete example of this may be the ubiquitous x86 assemblers from various vendors. Most of them are able to perform jump instruction replacements, long jumps replaced by short or relative jumps, in any number of passes, on request. Others may even do simple rearrangement or insertion of instructions, such as some assemblers for RISC architectures that can help optimize a sensible instruction scheduling to exploit the CPU pipeline as efficiently as possible. Like early programming languages such as Fortran, ALGOL, COBOL and Lisp, assemblers have been available since the 1950s and the first generations of text-based computer interfaces. However, assemblers came first as they are far simpler to write than compilers for high-level languages. This is because each mnemonic along with the addressing modes and operands of an instruction translates rather directly into the numeric representations of that particular instruction, without much context or analysis. There have also been several classes of translators and semi-automatic code generators with properties similar to both assembly and high-level languages, with SPID code as perhaps one of the better-known examples.
Number of passes.
There are two types of assemblers based on how many passes through the source are needed to produce the executable program. One-pass assemblers go through the source code once. Any symbol used before it is defined will require errata at the end of the object code, or, at least, no earlier than the point where the symbol is defined, telling the linker or the loader to go back, and overwrite a placeholder which had been left where the as yet undefined symbol was used. Multi-pass assemblers create a table with all symbols and their values in the first passes, then use the table in later passes to generate code. In both cases, the assembler must be able to determine the size of each instruction on the initial passes in order to calculate the addresses of subsequent symbols. This means that if the size of an operation referring to an operand defined later depends on the type or distance of the operand, the assembler will make a pessimistic estimate when first encountering the operation, and if necessary pad it with one or more no-operation instructions in a later pass or the errata. In an assembler with peephole optimization, addresses may be recalculated between passes to allow replacing pessimistic code with code tailored to the exact distance from the target. The original reason for the use of one-pass assemblers was speed of assembly. Often a second pass would require rewinding and rereading a tape or rereading a deck of cards. With modern computers this has ceased to be an issue. The advantage of the multi-pass assembler is that the absence of errata makes the linking process, or the program load of the assembler directly produces executable code, faster.
High-level assemblers.
More sophisticated high-level assemblers provide language abstractions such as advanced control structures, high-level procedure function declarations and invocations, high-level abstract data types, including structures, records, unions, classes, and sets, sophisticated macro processing, although available on ordinary assemblers since the late 1950s for IBM 700 series and since the 1960s for IBM/360, amongst other machines. Object-oriented programming features such as classes, objects, abstraction, polymorphism, and inheritance. See language design below for more details.
Assembly language.
A program written in assembly language consists of a series of mnemonic, processor instructions and meta statements, known variously as directives, pseudo-instructions and pseudo-ops, comments and data. Assembly language instructions usually consist of an opcode mnemonic followed by a list of data, arguments or parameters. These are translated by an assembler into machine language instructions that can be loaded into memory and executed. For example, the instruction below tells an x86/IA32 processor to move an immediate 8-bit value into a register. The binary code for this instruction is 10,110 followed by a 3-bit identifier for which register to use. The identifier for the AL register is 000, so the following machine code loads the AL register with the data 0110001. This binary computer code can be made more human-readable by expressing it in hexadecimal as follows. Here, BO means move a copy of the following value into AL, and 61 is a hexadecimal representation of the value 0110001, which is 97 in decimal. Intel assembly language provides the mnemonic MOV, an abbreviation of move, for instructions such as this, so the machine code above can be written as follows in assembly language, complete with an explanatory comment if required, after the semicolon. This is much easier to read and to remember. In some assembly languages the same mnemonic such as MOV may be used for a family of related instructions for loading, copying and moving data, whether these are immediate values, values in registers, or memory locations pointed to by values in registers. Other assemblers may use separate opcodes such as L for move memory to register, street for move register to memory, LR for move register to register, MVI for move immediate operand to memory, etc. The Intel opcode 10,110,000, BO, copies an 8-bit value into the AL register, while 10,110,001, B1, moves it into CL and 10,110,010, B2, does so into DL. Assembly language examples for these follow. The syntax of MOV can also be more complex as the following examples show. In each case, the MOV mnemonic is translated directly into an opcode in the ranges 88-AD, AOA3, BOB8, C6 or C7 by an assembler, and the programmer does not have to know or remember which. Transforming assembly language into machine code is the job of an assembler, and the reverse can at least partially be achieved by a disassembler. Unlike high-level languages, there is usually a one-to-one correspondence between simple assembly statements and machine language instructions. However, in some cases, an assembler may provide pseudo-instructions, essentially macros, which expand into several machine language instructions to provide commonly needed functionality. For example, for a machine that lacks a branch of greater or equal instruction, an assembler may provide a pseudo-instruction that expands to the machine's set if less than, and branch of 0, on the result of the set instruction. Most full-featured assemblers also provide a rich macro language, discussed below, which is used by vendors and programmers to generate more complex code and data sequences. Each computer architecture has its own machine language. Computers differ in the number and type of operations they support, in the different sizes and numbers of registers, and in the representations of data in storage. While most general-purpose computers are able to carry out essentially the same functionality, the ways they do so differ. The corresponding assembly languages reflect these differences. Multiple sets of mnemonics or assembly language syntax may exist for a single instruction set, typically instantiated in different assembler programs. In these cases, the most popular one is usually that supplied by the manufacturer and used in its documentation.
Language design. Basic elements.
There is a large degree of diversity in the way the authors of assemblers categorize statements and in the nomenclature that they use. In particular, some describe anything other than a machine mnemonic or extended mnemonic as a pseudo-operation, pseudo-op. A typical assembly language consists of three types of instruction statements that are used to define program operations: opcode mnemonics, data sections, assembly directives.
Opcode mnemonics and extended mnemonics.
Instructions, statements, in assembly language are generally very simple, unlike those in high-level language. Generally, a mnemonic is a symbolic name for a single executable machine language instruction, an opcode, and there is at least one opcode mnemonic defined for each machine language instruction. Each instruction typically consists of an operation or opcode plus 0 or more operands. Most instructions refer to a single value, or a pair of values. Operands can be immediate, value coded in the instruction itself, registers specified in the instruction or implied, or the addresses of data located elsewhere in storage. This is determined by the underlying processor architecture. The assembler merely reflects how this architecture works. Extended mnemonics are often used to specify a combination of an opcode with a specific operand. For example, the System/360 assemblers use B as an extended mnemonic for BC with a mask of 15 and NOP, NO operation do nothing for one step, for BC with a mask of 0. Extended mnemonics are often used to support specialized uses of instructions, often for purposes not obvious from the instruction name. For example, many CPUs do not have an explicit NOP instruction, but do have instructions that can be used for the purpose. In 8086 CPUs the instruction XCHG-AX, AX is used for NOP, with NOP being a pseudo-opcode to encode the instruction XCHG-AX, AX. Some disassemblers recognize this and will decode the XCHG-AX, AX instruction as NOP. Similarly, IBM assemblers for System/360 and System/370 use the extended mnemonics NOP and NOPR for BC and BCR with 0 masks. For the SPARC architecture, these are known as synthetic instructions. Some assemblers also support simple built-in macro instructions that generate 2 or more machine instructions. For instance, with some Z80 assemblers the instruction LDHL, BC is recognized to generate LDL, C followed by LDH, B. These are sometimes known as pseudo-opcodes. Mnemonics are arbitrary symbols. In 1985 the IEEE published Standard 694 for a uniform set of mnemonics to be used by all assemblers. The standard has since been withdrawn.
Data directives.
There are instructions used to define data elements to hold data and variables. They define the type of data, the length and the alignment of data. These instructions can also define whether the data is available to outside programs, programs assembled separately, or only to the program in which the data section is defined. Some assemblers classify these as pseudo-ops.
Assembly directives.
Assembly directives, also called pseudo-opcodes, pseudo-operations or pseudo-ops, are instructions that are executed by an assembler at assembly time, not by a CPU at runtime. The names of pseudo-ops often start with a dot to distinguish them from machine instructions. Pseudo-ops can make the assembly of the program dependent on parameters input by a programmer, so that one program can be assembled different ways, perhaps for different applications. Or, a pseudo-op can be used to manipulate presentation of a program to make it easier to read and maintain. Another common use of pseudo-ops is to reserve storage areas for runtime data and optionally initialize their contents to known values. Symbolic assemblers let programmers associate arbitrary names, labels or symbols, with memory locations and various constants. Usually, every constant and variable is given a name so instructions can reference those locations by name, thus promoting self-documenting code. In executable code, the name of each subroutine is associated with its entry point, so any calls to a subroutine can use its name. Inside subroutines, GOTO destinations are given labels. Some assemblers support local symbols which are lexically distinct from normal symbols, for example, the use of $10 as a GOTO destination. Some assemblers, such as NASM, provide flexible symbol management, letting programmers manage different namespaces, automatically calculate offsets within data structures, and assign labels that refer to literal values or the result of simple computations performed by the assembler. Labels can also be used to initialize constants and variables with relocatable addresses. Assembly languages, like most other computer languages, allow comments to be added to programs' source code that will be ignored during assembly. Judicious commenting is essential in assembly language programs, as the meaning and purpose of a sequence of binary machine instructions can be difficult to determine. It should be noted that the raw, uncommented, assembly language generated by compilers or disassemblers is quite difficult to read when changes must be made.
Macros.
Many assemblers support predefined macros, and others support programmer-defined, and repeatedly redefinable, macros involving sequences of text lines in which variables and constants are embedded. This sequence of text lines may include opcodes or directives. Once a macro has been defined, its name may be used in place of a mnemonic. When the assembler processes such a statement, it replaces the statement with the text lines associated with that macro, then processes them as if they existed in the source code file, including, in some assemblers, expansion of any macros existing in the replacement text. Note that this definition of macro is slightly different from the use of the term in other contexts, like the C programming language. C macros created through the defined directive typically are just one line, or a few lines at most. Assembler macro instructions can be lengthy programs by themselves, executed by interpretation by the assembler during assembly. Since macros can have short names but expand to several or indeed many lines of code, they can be used to make assembly language programs appear to be far shorter, requiring fewer lines of source code, as with higher-level languages. They can also be used to add higher levels of structure to assembly programs, optionally introduce embedded debugging code via parameters and other similar features. Macro assemblers often allow macros to take parameters. Some assemblers include quite sophisticated macro languages, incorporating such high-level language elements as optional parameters, symbolic variables, conditionals, string manipulation, and arithmetic operations, all usable during the execution of a given macro, and allowing macros to save context or exchange information. Thus a macro might generate numerous assembly language instructions or data definitions, based on the macro arguments. This could be used to generate record-style data structures or unrolled loops, for example, or could generate entire algorithms based on complex parameters. An organization using assembly language that has been heavily extended using such a macros suite can be considered to be working in a higher-level language, since such programmers are not working with a computer's lowest-level conceptual elements. Macros were used to customize large-scale software systems for specific customers in the mainframe era and were also used by customer personnel to satisfy their employers' needs by making specific versions of manufacturer operating systems. This was done, for example, by systems programmers working with IBM's Conversational Monitor System/Virtual Machine, VMCMS, and with IBM's real-time transaction processing add-ons, Customer Information Control System (CICS), and ACPTPF, the airline financial system that began in the 1970s and still runs many large computer reservation systems, CRS, and credit card systems today. It was also possible to use solely the macro-processing abilities of an assembler to generate code written in completely different languages, for example, to generate a version of a program in COBOL using a pure macro-assembler program containing lines of COBOL code inside assembly time operators instructing the assembler to generate arbitrary code. This was because, as was realized in the 1960s, the concept of macro-processing is independent of the concept of assembly, the former being in modern terms more word processing, text processing, than generating object code. The concept of macro-processing appeared, and appears, in the C programming language, which supports preprocessor instructions to set variables, and make conditional tests on their values. Note that unlike certain previous macroprocessors inside assemblers, the C preprocessor was not Turing-complete because it lacked the ability to either loop or goto, the latter allowing programs to loop. Despite the power of macroprocessing, it fell into disuse in many high-level languages, major exceptions being C, C++ and PLI, while remaining a perennial for assemblers. Macroparameter substitution is strictly by name. At macroprocessing time, the value of a parameter is textually substituted for its name. The most famous class of bugs resulting was the use of a parameter that itself was an expression in not a simple name when the macro writer expected a name. In the macro, foo macro load AB, the intention was that the caller would provide the name of a variable, and the global variable or constant B would be used to multiply A. If foo is called with the parameter AC, the macro expansion of load ACB occurs. To avoid any possible ambiguity, users of macroprocessors can parenthesize formal parameters inside macro definitions, or callers can parenthesize the input parameters.
Support for structured programming.
Some assemblers have incorporated structured programming elements to encode execution flow. The earliest example of this approach was in the Concept 14 macro set, originally proposed by Dr. H. D. Mills, March 1970, and implemented by Marvin Kessler at IBM's Federal Systems Division, which extended the S/360 macro assembler with IFLCNDIF and similar control flow blocks. This was a way to reduce or eliminate the use of GOTO operations in assembly code, one of the main factors causing spaghetti code in assembly language. This approach was widely accepted in the early 80s, the latter days of large-scale assembly language use. A curious design was A-Natural, a stream-oriented assembler for 8080/Z80 processors from Whitesmiths Limited, developers of the Unix-like Idris operating system, and what was reported to be the first commercial C compiler. The language was classified as an assembler, because it worked with raw machine elements such as opcodes, registers, and memory references. But it incorporated an expression syntax to indicate execution order. Parentheses and other special symbols, along with block-oriented structured programming constructs, controlled the sequence of the generated instructions. A-Natural was built as the object language of a C compiler, rather than for hand coding, but its logical syntax won some fans. There has been little apparent demand for more sophisticated assemblers since the decline of large-scale assembly language development. In spite of that, they are still being developed and applied in cases where resource constraints or peculiarities in the target system's architecture prevent the effective use of higher-level languages.
Use of assembly language. Historical perspective.
Assembly languages date to the introduction of the stored program computer. The EDSAC computer, 1949, had an assembler called initial orders featuring one-letter mnemonics. Nathaniel Rochester wrote an assembler for an IBM 701, 1954. SOAP, Symbolic Optimal Assembly Program, 1955, was an assembly language for the IBM 650 computer written by Stan Poley. Assembly languages eliminated much of the error-prone and time-consuming first-generation programming needed with the earliest computers, freeing programmers from tedium such as remembering numeric codes and calculating addresses. They were once widely used for all sorts of programming. However, by the 1980s, 1990s on microcomputers, their use had largely been supplanted by higher-level languages, in the search for improved programming productivity. Today assembly language is still used for direct hardware manipulation, access to specialized processor instructions, or to address critical performance issues. Typical uses are device drivers, low-level embedded systems, and real-time systems. Historically, numerous programs have been written entirely in assembly language. Operating systems were entirely written in assembly language until the introduction of the Burroughs MCP, 1961, which was written in ESPOL, an ALGOL dialect. Many commercial applications were written in assembly language as well, including a large amount of the IBM mainframe software written by large corporations. COBOL, Fortran and some PLI eventually displaced much of this work, although a number of large organizations retained assembly language application infrastructures well into the 90s. Most early microcomputers relied on hand-coded assembly language, including most operating systems and large applications. This was because these systems had severe resource constraints, imposed idiosyncratic memory and display architectures, and provided limited, buggy system services. Perhaps more important was the lack of first-class high-level language compilers suitable for microcomputer use. A psychological factor may have also played a role. The first generation of microcomputer programmers retained a hobbyist, wires and pliers attitude. In a more commercial context, the biggest reasons for using assembly language were minimal bloat, size, minimal overhead, greater speed, and reliability. Typical examples of large assembly language programs from this time are IBM PC DOS operating systems and early applications such as the spreadsheet program Lotus 1-2-3. Even into the 1990s, most console video games were written in assembly, including most games for the Mega Drive Genesis and the Super Nintendo Entertainment System. According to some industry insiders, the assembly language was the best computer language to use to get the best performance out of the Sega Saturn, a console that was notoriously challenging to develop and program games for. The popular arcade game NBA Jam, 1993, is another example. Assembly language has long been the primary development language for many popular home computers of the 1980s and 1990s, such as the Sinclair ZX Spectrum, Commodore 64, Commodore Amiga, and Atari ST. This was in large part because basic dialects on these systems offered insufficient execution speed, as well as insufficient facilities to take full advantage of the available hardware on these systems. Some systems even have IDEs with highly advanced debugging and macro facilities. The assembler for the VIC-20 was written by Don French and published by French Silk. At 1,639 bytes in length, its author believes it is the smallest symbolic assembler ever written. The assembler supported the usual symbolic addressing and the definition of character strings or hex strings. It also allowed address expressions which could be combined with addition, subtraction, multiplication, division, logical OR, and exponentiation operators.
Current usage.
There have always been debates over the usefulness and performance of assembly language relative to high-level languages. Assembly language has specific niche uses where it is important. See below. Assembler can be used to optimize for speed or optimize for size. In the case of speed optimization, modern optimizing compilers are claimed to render high-level languages into code that can run as fast as handwritten assembly, despite the counterexamples that can be found. The complexity of modern processors and memory subsystems makes effective optimization increasingly difficult for compilers, as well as assembly programmers. Moreover, and to the dismay of efficiency lovers, increasing processor performance has meant that most CPUs sit idle most of the time, with delays caused by predictable bottlenecks such as cache misses, I/O operations and paging. This has made raw code execution speed a non-issue for many programmers. There are some situations in which developers might choose to use assembly language. A standalone executable of compact size is required that must execute without recourse to the runtime components or libraries associated with a high-level language. This is perhaps the most common situation. For example, firmware for telephones, automobile fuel and ignition systems, air conditioning control systems, security systems, and sensors, code that must interact directly with the hardware, for example in device drivers and interrupt handlers, programs that need to use processor-specific instructions not implemented in a compiler. A common example is the bitewise rotation instruction at the core of many encryption algorithms, programs that create vectorized functions for programs in higher-level languages such as C. In the higher-level language, this is sometimes aided by compiler intrinsic functions which map directly to SIMD mnemonics, but nevertheless result in a one-to-one assembly conversion specific for the given vector processor. Programs requiring extreme optimization, for example an inner loop in a processor-intensive algorithm. Game programmers take advantage of the abilities of hardware features in systems, enabling games to run faster. Also, large scientific simulations require highly optimized algorithms, for example linear algebra with BLAS or discrete cosine transformation, for example SIMD assembly version from X264. Situations where no high-level language exists, on a new or specialized processor, for example, programs that need precise timing such as real-time programs such as simulations, flight navigation systems, and medical equipment. For example, in a fly-by-wire system, telemetry must be interpreted and acted upon within strict time constraints. Such systems must eliminate sources of unpredictable delays, which may be created by some interpreted languages, automatic garbage collection, paging operations, or preemptive multitasking. However, some higher-level languages incorporate runtime components and operating system interfaces that can introduce such delays. Choosing assembly or lower-level languages for such systems gives programmers greater visibility and control over processing details. Cryptographic algorithms that must always take strictly the same time to execute, preventing timing attacks, real-time programs such as simulations, flight navigation systems, and medical equipment. For example, in a fly-by-wire system, telemetry must be interpreted and acted upon within strict time constraints. Such systems must eliminate sources of unpredictable delays, which may be created by some interpreted languages, automatic garbage collection, paging operations, or preemptive multitasking. However, some higher-level languages incorporate runtime components and operating system interfaces that can introduce such delays. Choosing assembly or lower-level languages for such systems gives programmers greater visibility and control over processing details. Cryptographic algorithms that must always take strictly the same time to execute, preventing timing attacks, situations where complete control over the environment is required. In extremely high-security situations where nothing can be taken for granted, computer viruses, bootloaders, certain device drivers, or other items very close to the hardware or low-level operating system, instruction set simulators for monitoring, tracing and debugging where additional overhead is kept to a minimum, reverse engineering and modifying program files such as existing binaries that may or may not have originally been written in a high-level language. For example when trying to recreate programs for which source code is not available or has been lost, or cracking copy protection of proprietary software. Video games, also termed ROM hacking, which is possible via several methods. The most widely employed is altering program code at the assembly language level, existing binaries that may or may not have originally been written in a high-level language. For example when trying to recreate programs for which source code is not available or has been lost, or cracking copy protection of proprietary software. Video games, also termed ROM hacking, which is possible via several methods. The most widely employed is altering program code at the assembly language level, self-modifying code, to which assembly language lends itself well, games and other software for graphing calculators. Assembly language is still taught in most computer science and electronic engineering programs. Although few programmers today regularly work with assembly language as a tool, the underlying concepts remain very important. Such fundamental topics as binary arithmetic, memory allocation, stack processing, character set encoding, interrupt processing, and compiler design would be hard to study in detail without a grasp of how a computer operates at the hardware level. Since a computer's behavior is fundamentally defined by its instruction set, the logical way to learn such concepts is to study an assembly language. Most modern computers have similar instruction sets. Therefore, studying a single assembly language is sufficient to learn, I, the basic concepts. 2. To recognize situations where the use of assembly language might be appropriate. And 3. To see how efficient executable code can be created from high-level languages. This is analogous to children needing to learn the basic arithmetic operations, for example, long division, although calculators are widely used for all except the most trivial calculations.
Typical applications.
Assembly language is typically used in a system's boot code, BIOS on IBM-compatible PC systems, and CP/M, the low-level code that initializes and tests the system hardware prior to booting the operating system, and is often stored in ROM. Some compilers translate high-level languages into assembly first before fully compiling, allowing the assembly code to be viewed for debugging and optimization purposes. Relatively low-level languages, such as C, allow the programmer to embed assembly language directly in the source code. Programs using such facilities, such as the Linux kernel, can then construct abstractions using different assembly language on each hardware platform. The system's portable code can then use these processor-specific components through a uniform interface. Assembly language is valuable in reverse engineering. Many programs are distributed only in machine code form, which is straightforward to translate into assembly language, but more difficult to translate into a higher-level language. Tools such as the interactive disassembler make extensive use of disassembly for such a purpose. Assemblers can be used to generate blocks of data, with no high-level language overhead, from formatted and commented source code, to be used by other code.
Related terminology.
Assembly language or assembler language is commonly called assembly, assembler, ASM, or symbolic machine code. A generation of IBM mainframe programmers called it ALC for assembly language code or BAL for basic assembly language. Calling the language assembler might be considered potentially confusing and ambiguous, since this is also the name of the utility program that translates assembly language statements into machine code. However, this usage has been common among professionals and in the literature for decades. Similarly, some early computers called their assembler their assembly program, the computational step where an assembler is run, including all macro processing, is termed assembly time. The assembler is said to be assembling the source code. The use of the word assembly dates from the early years of computers, cf short code, SPID code. A cross-assembler, see also cross-compiler, is an assembler that is run on a computer or operating system of a different type from the system on which the resulting code is to run, the target system. Cross-assembling may be necessary if the target system cannot run an assembler itself, as is typically the case for small embedded systems. The computer on which the cross-assembler is run must have some means of transporting the resulting machine code to the target system. Common methods involve transmitting an exact byte-by-byte copy of the machine code or an ASCII representation of the machine code in a portable format, such as Motorola or Intel hexadecimal, through a compatible interface to the target system for execution. An assembler directive or pseudo-opcode is a command given to an assembler directing it to perform operations other than assembling instructions. Directives affect how the assembler operates and may affect the object code, the symbol table, the listing file, and the values of internal assembler parameters. Sometimes the term pseudo-opcode is reserved for directives that generate object code, such as those that generate data. A meta-assembler is a program that accepts the syntactic and semantic description of an assembly language, and generates an assembler for that language.
Further details.
For any given personal computer, mainframe, embedded system, and game console, both past and present, at least one, possibly dozens, of assemblers have been written. For some examples, see the list of assemblers. On Unix systems, the assembler is traditionally called as, although it is not a single body of code, being typically written anew for each port. A number of Unix variants use GAS. Within processor groups, each assembler has its own dialect. Sometimes, some assemblers can read another assembler's dialect, for example, TASM can read old MASM code, but not the reverse. FASM and NASM have similar syntax, but each support different macros that could make them difficult to translate to each other. The basics are all the same, but the advanced features will differ. Also, assembly can sometimes be portable across different operating systems on the same type of CPU. Calling conventions between operating systems often differ slightly or not at all, and with care it is possible to gain some portability in assembly language, usually by linking with a C library that does not change between operating systems. An instruction set simulator can process the object code/binary of any assembler to achieve portability even across platforms with an overhead no greater than a typical bytecode interpreter. This is similar to use of microcode to achieve compatibility across a processor family. Some higher-level computer languages, such as C and Ball and Pascal, support inline assembly where sections of assembly code, in practice usually brief, can be embedded into the high-level language code. The fourth language commonly contains an assembler used in code words. An emulator can be used to debug assembly language programs.
Example listing of assembly language source code.
The following is a partial listing generated by the NASM, an assembler for 32-bit Intel x86 CPUs. The code is for a subroutine, not a complete program. The first column, from the left, is simply the line number in the listing and is otherwise meaningless. The second column is the relative address, in hex, of where the code will be placed in memory. The third column is the actual compiled code. For instance, B9 is the x86 opcode for the MOVECX instruction. FFFFFFFF is the value. 1 and 2's complement binary form. Names suffixed with colons are symbolic labels. The labels do not create code, they are simply a way to tell the assembler that those locations have symbolic names. The done label is only present for clarity of where the program ends, it does not serve any other purpose. Prefixing a period on a label is a feature of the assembler, declaring the label as being local to the subroutine.